All right, here's what we were going to do right at the end of class on Monday, day 16, before we either ran out of time or had technical difficulties. The general idea is that we want to talk about probability distributions. So if a random situation has some number of outcomes, we can talk about the probability of each of those outcomes and think of the whole thing as a distribution, like we did with our quantitative variables back in the first couple weeks of the course. All right, an example of this. In class today, Monday, we played a game where we rolled a die and we got points based off of what number showed on that die, unless it was a 5, in which case it was 0. All right, so right now I'm only talking about one die roll, not the whole game where there are multiple rounds or anything. We're just focusing on this one die roll. So the question is, how many points might we get? It's like, well, if we roll this and get a 1, then we get 1 point. And so we can mark how likely that is with a bar, right? So because each outcome, each of the 6 options is equally likely, there is a 1/6 chance of getting a 1, there's a 1/6 chance of getting a 2, 3, or 4. There's a 1/6 chance of rolling a 5. But remember, rolling a 5 was 0 points. And then there was a 1/6 chance of rolling a 6, which was 6 points. So here x is the number of points that we get from a die roll. And x can be any one of these numbers, so 0 through 6. The probability of it being 5 is 0, but we're still going to include it on our graph. So on the y-axis, we are writing the probability of each of these things occurring. And the notation for this is a little bit weird. We're writing the probability that our random variable x, which by the way is a capital X, the probability that this random variable equals some number. So for example, we might say the probability that our random variable equals 3, the probability that we get 3 points, is 1/6. The way that we write that in the generic way is the probability that x equals x. It's the probability that our random variable equals a specific value, probability that big X equals little x, which is certainly a strange thing to see. Here is it written out not sideways, probability x equals x, is just sort of the probability that our random variable equals something. We often replace the little x with some specific number. Given a distribution like this, we might want to know, all right, what's the middle? What's the average number of points we would get with a single die roll? Well, that is the expected value, and that's just going to be the weighted average of each of these possible outcomes. Formula-wise, the expected value is the sum of the number of points that you get for a particular outcome times the probability that we get that outcome. So again, the formatting for this certainly looks weird, but what we're doing in this particular case is we're adding up each of the different point values times their probability. So in this case, we would get 0 times 1/6 plus 1 times 1/6, etc., which should end up being 2 2/3. So on average, each die roll should give us 2 2/3 more points. Well, we call this an expected value. Do we really expect the die roll to be, 2 2/3 points? No. This value is actually impossible, but this is just an average. All right. So just like we do with a lot of other distributions, we'll often call this mu for the mean. So either mu or e of x is a way of talking about the expected value or the average of this distribution. The other question that we might ask about a distribution is, what is the spread? So in this case, we're interested in what the standard deviation is, or first we're going to talk about what the variance of our random variable is. And the way that we're going to find this should look very familiar. We're taking the sum of how far away each of the points are. So in this case, how far away 0 is or 1 is from the mean. We're going to look at those differences squared, weighted by their probabilities. So in a formula, this is the sum of x minus mu, so how far away from the mean we are, squared times the probability of that particular value. So going through the start of this would be 0 minus 2 2/3 squared times 1/6 plus 1 minus 2 2/3 squared times 1/6, etc., which should end up being 3.89. Now, variance is great, and we will use it because it makes a lot of calculations a little bit easier, but when we're trying to understand a distribution, standard deviation gives us sort of a better sense of what's happening. So just like before, the standard deviation, which we're going to denote as as either sigma or SD of x, this is going to be the square root of the variance. So in our example here, this is going to end up being 1.97, I believe. All right, so that's telling us that the standard deviation of this distribution is 1.97. The mean was 2 2/3. So we can say that the mean is right about there, and that the standard deviation is almost 2.